All right, we're going to talk about what half-life is and how to calculate that. Half-life is defined as the amount of time it takes for half of a radioactive sample to decay. So think about taking a less stable radioisotope and decaying it to a more stable. The half-life is not dependent on the amount in the sample, the temperature, or the pressure. So what's really neat about this is if you can calculate the half-life, it is a really great way to measure independent of other variables how old something is. If you have a long half-life, usually these isotopes are naturally occurring. Think about carbon-14, which has a half-life of 5,730 years, or uranium-235, which has a half-life of 7 times 10 to the 8th years. That's a huge amount for a half-life. The shorter half-life radioisotopes are typically artificially produced, although this is not always the case. So technetium-99m has a 6-hour half-life, iodine-131, it has a half-life of 8 days. Let's take a look at a sample problem. So iodine-131, we're told, has a half-life of 8 days. We start with 40 milligrams. They want to know how much is left after 3 half-lives. So this may sound kind of dumb, but I just want to divide it by 2 3 times. And that would be the logical way to approach this. So I start with my 40 milligrams, divide by 2, that's 1 half-life, 20 milligrams. Divide by 2 again, that's 2 half-lives, 10 milligrams. Divide by 2 one last third time, the answer is 5 milligrams. So don't be scared. If it is this simple, go ahead and divide by 2 each time. I will say there will be problems where you're calculating 20 half-lives or 37 half-lives. And if this is the case, please, for the love of everything, do not try to divide by 2 37 times. You're going to lose count somewhere around 18, and you're just going to have to start over again. So when you're faced with a calculation where you're like, man, that's way too many half-lives to just do manually by dividing by 2, you're going to use this equation where n is your amount of material and x is the number of half-lives. So in the sample problem that we just did, 40 milligrams is our amount of material, and we are going to divide that by 2 raised to the number of half-lives, which is 3, and you should get the same answer for that. Remember to use parentheses when you are putting this into your calculator. Very important to always use parentheses. So radioactive dating uses the steady decay of an unstable nucleus to a stable one to give a time frame for how old an object is. So we have archaeological dating and we have geologic dating. Let's start with archaeological dating. This uses carbon-14, which is a radioisotope that decays to carbon-12. As we said before, the half-life is 5,730 years, and we use this to estimate the age of the artifact. Keep in mind for archaeological dating, your artifacts have to be organic, meaning they're carbon containing, not that they were grown without pesticides. They stole that term from us, but that is another conversation for another day. So plants, animals, something that's been alive at some point, you can use carbon dating to figure out how old this artifact is. So the way this works is that plants and animals are taking in carbon-14 as CO2. Now, that's not to say that you and I as animals are taking in CO2. Plants are taking in CO2, converting those carbons with the carbon-14 to glucose. We eat the plants. That's how we get it in. The carbon-14 is going to decay. When an organism dies, they're no longer taking in carbon-14. So the carbon-14 upon death is going to start to decay without being replenished, and the concentration of carbon-14 is going to decrease. This is what allows us to figure out how old something is, because we can compare carbon-14 amounts in the artifact to carbon-12 amounts, and we can estimate the age of the artifact. And I love this little image down here. So this is our artifact that we're trying to age. So we know that plants are going to absorb carbon during photosynthesis. Our poor turkey that's going to have to die, or we can't age it, is going to take in that plant material. So it's taking in carbon-14 its entire life until it dies, and then it stops taking it in. Evidently, some human made a tool out of his leg bone. So the carbon-14 in this artifact is going to start to decay at a consistent rate. We can then take a sample of that and we can measure how much carbon-14 is left in the bone compared to how much carbon-12 there is and estimate the age of the artifact. Geologic dating is used for not artifacts, but used for materials that are very old and inorganic. So when I say inorganic, not carbon containing, they weren't alive, think about rocks. The tricky part here is fossils would also be, you could date fossils using geologic dating as well, and that is because inorganic material has replaced all the organic materials. So it's essentially a rock at this point that you're dating. Geologic dating uses uranium-238, it uses lead-206. These are radioisotopes that have half-lives of 4.5 billion years. You can see this list of these useful ranges based on the half-life. We're talking about species or specimens that have been around for the millions and billions of years rather than just thousands. So that's how we age the dinosaur fossils or rocks that we find. All right, let's practice. If the amount of a radioactive element decreases from 2.4 grams to 0.30 grams in 12 days, what is its half-life? So this is a good example of, man, I could divide by 2 a couple times until I get to that value and then count how many times I divided to solve this problem. So let's do 2.4 divided by 2 is 1.2. That's 1 half-life. We're not at 0.3, so we're going to keep going. Divide by 2 again, you get 0.60. So that's your second half-life. Divide by 2 again, now we get 0.3. But it didn't ask me how many half-lives were there. There were 3. It says this happens over the course of 12 days. What is the half-life? So 12 days divided by 3 tells us that a half-life is 4 days. In our next example, we're told the amount of a radioactive element decreases from 0.36 grams to 90 milligrams in 22 minutes. What is its half-life? Okay, this looks really straightforward at first glance, like I'm just going to use the same approach as last time, but it's not. Here we have a difference in units, and be very careful of this, okay? That number 90 is bigger than 0.36, so that should be a red flag because your amount should be decreasing. So I'm going to go ahead and convert this to grams. So I'm going to move the decimal 3 to the left or divide by 1,000. 1, 2, 3. So this is actually 0.090 grams. So now I'm ready, since we're in the same unit, to start dividing by 2. My first half-life gives me 0.18 grams. Divide by 2 again, it's my second half-life, you get 0.090 grams. Winner, winner, chicken dinner, we've made it. So we know that we have 2 half-lives that have happened. This is happening over the course of 22 minutes. They want to know what's the half-life. Well, 22 divided by 2 is 11 minutes. So our half-lives are 11 minutes because there are only 2 half-lives that occurred in that time frame with the amount that we were given.